Welcome to Lecture 2.8, Set-theoretic Proofs. I'll motivate this by pointing out that thus far we've come across statements like the following. For any sets A, B, and C, A take away B is contained in B. A intersect B union C equals A intersect B union A intersect C. That's the distributive property. And then if A union B is contained in A union C, then B has to be contained in C. Now, we haven't seen exactly these statements, not necessarily, but we've seen statements like these. And thus far, our primary method of proof, and that is in quotes, which usually means that I'm lying, because it's not really a proof, has been by examining a Venn diagram. So here's two examples of that, and I will actually quote-unquote prove these two statements in this manner. So the first one says that A take away B is contained in B. So let's draw what that is. So A take away B, again, remember I like to call it that just because it's unambiguous. So A take away B are the things that are in A but not in B. So that's this little region here. I'm not going to draw it in too carefully. Don't really need to, you get the idea. And so if we take A and then we subtract that blue area, which is right here, then what does that look like? Well, that's this here, and that's definitely contained in B, which is the circle here, right? Convincing argument? Yes, but a proof? Not quite. So, or at least not a rigorous proof. So the second one is distributive law. So let's verify that this works. So the intersection of A and B union C. So B union C is, let's see what color I want to use for that now. That's every. How about if I do this? That's everything that's inside here. And if I take the intersection of A with that, then I get this little blue region here. And then the right-hand side is A intersect B union A intersect C. So A intersect B is that green area, and A intersect C is this yellow area. And so those are the same. Again, not quite a formal, rigorous proof, but it's hopefully a convincing argument. Now let me finish by verifying this last one. It says, so let me draw A. It says if A union B is contained in A union C, then B has to be contained in C. So if this is A union B, and for this to be contained in A union C, then well, then this area is not covered by A, so C is going to have to be so C will have to be something like this, and then B has to be contained in C. Okay, convinced? Well, you shouldn't be, because did you catch the lie that I just gave you? So hopefully you caught it when I did it. It was in the last one. If this is A and this is B, well then, what if I did something like that? What if this is C? So this is an example where A union B is contained in A union C, but B is not contained in C. Or something else I could have done is I could have drawn A like this, and B inside of it, and then C could have been out there. So this is a picture that would not necessarily come up if you're just drawing an arbitrary Venn diagram, because you're expecting there to be arbitrary, all possible intersections, but you could have something special like this. So sometimes your picture is not as general as it needs to be. Okay, so again, let this be a cautionary tale for a proof by picture and to motivate the ideas in this lecture, which is how do you rigorously formalize a proof to verify statements like this. And of course, this last one is definitely not true. Now, one thing that we do know how to do is proof statements using propositional logic. So we'll warm up now by converting a bunch of set-theoretic statements into and, or, and not. So let's begin with this first one. If X is in the union of A and B, that means that X is in A or X is in B. Okay, so I'll usually be putting the next statement up well in advance so you can take a look at it and try to figure out what it is before I tell you. And I encourage you to pause the video if you need a few more seconds. So X is not in A union B is equivalent to X is not in A and X is not in B. Okay, the next one, you get the hang of this? X is in A intersect B is equivalent to X is in A and X is in B. Next, X is not in A intersect B is equivalent to X is not in A or X is not in B. Next, X is in A take away B is equivalent to X is in A and X is not in B. Now, if X is not in A take away B, that is equivalent to X is not in A or X is in B. Let's draw pictures of those last ones just to verify. So if this is A and this is B, so if X is, this last one, if X is in A take away B, I think that one is a little bit easier, is that X is in A and X is not in B. But the next one, if X is not in A take away B, then it could be that X is somewhere out here. X is not in A. Or it could mean that X is in B. It could be there or there as well. So really either X is not in A or X is in B will cover all of it. Our next one is X is in the Cartesian product A cross B. That is equivalent to X being the ordered pair little a, little b for some little a in big A and some little b in big B. Okay, next, A is contained in B, or A is a subset of B. That is equivalent to if X is in A, then X is in B. Or sometimes we'll write X in A, if this, then that, with that arrow. But I think it's easier just to write if then. And finally, here's the one that I want to focus on, is if A and B are equal to each other, that means that A is contained in B and B is contained in A. So if A is contained in B, that is this statement here. So if we want to prove that A is equal to B, then to prove this first one, we have to take an arbitrary element in A and prove that it is in B. And then for this second condition, we have to say that if X is in B, take an arbitrary element in B, then X is in A. Okay, so that's going to be one of the main new techniques of this lecture. In this lecture, we'll actually see 3 techniques for proving equality of two sets, A and B. First, we will see that sometimes we can explicitly write down a formula for A. So we can write down A is a set of all elements in the universe such that some conditions hold, and then we can write down a chain of equalities to end up with a similar condition that is equal to B. That's the more straightforward or direct way to do it. A second method, which I described above, is we can show that A is contained in B and A contains B. Show those things separately. And finally, sometimes we can show this indirectly, in other words, by contrapositive or by contradiction. Recall that we have seen a number of basic laws of propositional calculus in a previous lecture. I think it was 2.3, equivalence and implication. And each of these laws has a so-called dual law that is obtained by exchanging the symbols and with or and 0 with 1. So since we've seen these before, I'll be brief in summarizing these. So the first one is a commutativity, which says that P or Q is equivalent to Q or P, or the dual law is P and Q is equivalent to Q and P. Now, it's not like one of these is commutativity, the other one is the dual. They are both dual to each other, so it was kind of arbitrary of which one I decided to put in this column. Same with associativity. So the associativity says P or Q or R is equivalent to P or Q or R. And the dual law is the same thing, just replace each or with an and. And the next is distributive law. Now this actually has a left and a right version. I just put the left one. The right one is analogous. I'll let you take a few moments to figure out what that is. But this one says that P and Q or R is equivalent to P and Q or P and R. So my pauses are indicating where the parentheses are. And then the dual law is, of course, P or Q and R is equivalent to P or Q and P or R. Next is identity. P or 0 is equivalent to P. And now the dual of this, you have to replace both the or with an and the 0 with a 1. So you get that P and 1 is equivalent to P. Negation says that P and not P is equivalent to 0. So P and not P can never be true and false. And the dual says that P is either true or false. P or not P is equivalent to 1. And I probably should go back to the previous one and say what they say in plain English. This says if you take an or statement that with 0, that doesn't actually change anything. And here, if you take an and statement with 1, that doesn't change anything either. Okay, that wasn't that interesting, I guess. Next one, idempotent, says P or P is equivalent to P. And the dual is that P and P is equivalent to P. The null law is P and false is equivalent to, is always false. And the dual of that is that if you take an and or an or statement with 1, you always get 1. Absorption is just P and P or Q is equivalent to P. And that P or, and the dual is P or P and Q is equivalent to P. Okay, so finally, De Morgan's laws, you know that not P or Q is not P and not Q, and not P and Q is equivalent to not P or not Q. The reason why I reviewed this is because we can turn each of these laws into an associated or corresponding law of set theory by replacing each P with a set A, each Q with B, each and symbol with intersection, each or with a union, each 0 with the empty set, each 1 with the universe, and finally each negation with a complement, and each equivalence with equals. Okay, so take a look at this table, and on 3, I'm going to switch it into a table for laws of set theory. Ready? 1, 2, okay, 3. And each of these laws below has a dual law, of course, obtained by exchanging the symbols intersection with union and the empty set with the universe. So, commutativity just says that A union B is B union A, and the same with intersection. Associativity, we've seen things like this before. A union B, union C is just A union B union C, and the same with intersections. Distributive laws are A, again, this is the left distributive law, A union B union C is equal to A intersect B union A intersect C. And here's the dual law. The identity just says that A union the empty set is just A, and A intersect the universe is A. Does make sense. The negation says that A intersect its complement is empty, and A union its complement is everything. The idempotent law says that A union A is A, and A intersect A is A. The null law says that A intersect the empty set is empty, and A union the whole thing is the whole thing. And the absorption laws say that A intersect A union B is equal to A, and A union A intersect B is equal to A. And then De Morgan's laws says the complement of A union B is A complement intersect B complement, and conversely, the complement of A intersect B is the union of A complement and B complement. Let's start by proving the distributive law, or at least the form of it that we saw on the first slide, two different ways. So there shouldn't be any ambiguity or uncertainty that this law is true, but we still haven't proved it formally. The only thing we've done is verified it with a Venn diagram and also showed how it arises from a law of propositional logic that we know by exchanging, again, and ors with unions and intersections. Neither of these are formal proofs. So here is that statement formally. For any sets A, B, and C, A intersect B union C is equal to A intersect B union A intersect C. Okay, so the first method we're going to do is just directly. And we will write out first the definition of the left-hand side, A intersect B union C. So by definition, that is the set of all elements in the universe that are in A and in B union C. So that's why I put that table that we had already seen before a few slides ago. Okay, next, I'm going to take this, I'm going to rewrite this to be equivalently by expanding out this X in B union C to be X in B or X in C. So in other words, this is the set of all X in the universe such that X is in A and X is in B or X is in C. And that's just from the definition of union. Okay, now let's apply the distributive law, which we know is true for logical expressions. And why is that true? Because we verified it using truth tables. So this is the set of all elements in the universe, X, such that X is in A and X is in B, or X is in A and X is in C. Okay, so now what? Now let's use the intersection on both of the definition of intersection on both of these things and go backwards. We will say that this first part is what it means for X to be in A intersect B, and this X is in A intersect C. Okay, so this is a set of all elements X in the universe such that X is in A intersect B, or X is in A intersect C, and that is the definition of the union of A intersect B with A intersect C. So in other words, that is a set of all X in U such that X is in A intersect B, union A intersect C, which by definition is what we want, the right-hand side, A intersect B, union A intersect C. So again, this first method, we just write out, we start with, let's say, the left-hand side, we write out a definition in set notation, and we tweak it step by step. Everything that we write is true, using laws that we know hold, and we end up with an expression for the right-hand side. Let's prove this using our second method, and we'll begin by taking an arbitrary element X in the left-hand side and showing that it has to exist in this right-hand side as well. So we'll denote that with this set containment symbol, and we'll say, let's let X be in A intersect B union C. And then what does that mean? That means then X is in A and X is in B union C, and either, I'm going to say B is in, sorry, not B, X is in B, X is in B, or 2X is in C. So case 1, so again, we already know that X is in A, but also, I'll put parentheses here just to be clear, also one of these things has to be the case. X is in B or X is in C. So case 1 is when X is in B. In that case, then since X is already in A, X is in A intersect B. Okay, so case 2 is, case 2 is that X is in C. In this case, we already know X is in A. Then X is in A, not A intersect C. Okay, so we have that either X is in A intersect B or X is in A intersect C, which means it is in the union of those two sets. So let's write that out. Then we conclude that X is in A intersect B, or X is in A intersect C, and that is equivalent, or that implies also equivalent to X being in the union of these two sets, A intersect B union A intersect C. Okay, so I didn't have to go in that much detail. I think it's sort of like writing code, or maybe writing comments for your code. Some people are more elaborate and include more details than others. But again, what's important is that I started with an arbitrary element in here, and I ended up with that, yes, that element is in the right-hand side. Okay, so now let's do the opposite. Let's take an arbitrary element in here. So let's let X be in A intersect B union A intersect C. And this means that either X is in A intersect B, or 2X is in A intersect C. So really, this proof can almost be done by just by reversing all of these arrows. But more on that later. Let's keep going. So if X is in A intersect B, and then so in both cases, X is in A. So, oops, I wrote that. Let me use the wrong other type of pen. Then X is in A, and either X is in B or X is in C, i.e. X you see X is in A intersect, because of the and, B or C, B union C. And there we go. We proved that direction as well. So notice that we could almost have, maybe rewritten this so everything here is really an if and only if. We really could have written this so X is in here is equivalent to this, which is equivalent to X being an A and these two cases, which is equivalent to this here. So, but it's just a little bit easier, I think, to to do it in 2 steps. Do not try to do too much. If you do too much, then it's a little bit too delicate. So start with the left-hand side, something on the left-hand side, show it's in the right-hand side, and vice versa. Sometimes establishing a theorem can lead right away to a follow-up result that we often call a corollary. So as an example of this, here's the theorem that we proved 2 different ways, the distributive law. A corollary is the following. For any sets A and B, A intersect B union A intersect B complement is equal to A. So, of course, this is something that is not too surprising. If we draw a little Venn diagram here, A and B, and we look at what this means, A intersect B is this little sector here, and A intersect complement of B is everything here, and that certainly looks like it's A, but as we've seen, pictures can be deceiving, so we could prove this using one of our other methods, like directly by taking something on the left-hand side and showing it's in the right-hand side and vice versa, but that's unnecessary. Notice that if we take this first theorem and we just set, or we plug in B complement in for C, then I claim that we're going to get this right here. Okay, so maybe you already see that, but let's write it up formally just to be for completeness. So let's let C equal to B complement. Then by the theorem, let's write down directly what we get. We get that A intersect B union B complement equals A intersect B union A intersect B complement. And now notice that B union B complement is equal to the universe. So we can write this as A intersect the universe, and of course that is just equal to A by one of our basic laws of set theory. And so this is exactly what we had to prove, and so that is the end of the proof. In many instances, such as the example that I showed you in this lecture of proving the distributive law, either of the 2 aforementioned methods work equally well. However, sometimes there really is no choice. Sometimes you have to use one method over the other. As an example of this, consider the following from linear algebra. If you haven't taken linear algebra, then that's fine. I will give you the necessary definitions. You probably won't feel as comfy with it as those of you who have taken it, but I think that's okay. Let V be a vector space over R. So if you don't know what this is, think of it just as a collection of vectors that is closed under the operation of addition and scalar multiplication. So a bunch of vectors, and if you add up any of those vectors or subtract them from each other or multiply by scalars, you get another vector in the set. So in your mind, you should think of like a line or a plane that goes through the origin. So something like this. If you have a plane, then any 2 vectors on this plane, if you add them up, you get another vector on the plane. And if you scale any vector by some scalar, you get another vector on the plane. So recall that the subspace spanned by a set of vectors S. Now S, I am not making any conditions on this. S could be finite or it could be infinite. But the subspace spanned by it, span just means generated. So it is literally the set of all vectors that can be written as this form. We say this is a linear combination, A1, S1 plus dot, 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 AK, SK, or AI. The AIs are the scalars. They are in are, and the SIs are the vectors. So you've seen things like this before. So things like 2. So if we have 1, 2, and 0, 3, then maybe 2 plus 4, 0, 3. This is a, so if 1, 2 lies on our plane and 0, 3 lies on our plane, then so does this linear combination. So this is 2, 4 plus 0, 12, which is 2, 16. Okay, so that's what the span of a subspace is. And I claim that for any subset S of vectors, finite or infinite, that the span of that subset is equal to the intersection of all subspaces W alpha that contain S. So this is the set containment symbol, and this less than or equal to means not just is it a subset of V, but it's a subspace of V. So here's how you should think about this. So the left-hand side, think of it as building the subspace from the bottom up. You're starting with nothing, then you're starting with the things in S, and you're seeing what those things generate just by taking finite sums. The right-hand side starts with subspaces and intersects them, shrinking them down. So it says, I don't know, maybe, let me draw a picture here. Maybe S is these collection of points. Maybe there's something else in there that, I don't know, maybe this is S. Well, the right-hand side says, take all of the subspace. This is a cartoon drawing. These don't look like vectors, obviously, but take all of the subspaces. Maybe this is W1, maybe this is W2, this is some other W alpha, and that if you intersect all of those, then what you actually get is the span. The actual subspace that you get is the span of S. So this one you're building from the top down. And here's another picture of it, maybe a little bit more realistic, an explicit example. Let's suppose that S is the ray starting at the origin going out some direction in R3. So that's S. That's not a subspace because it's not closed under scalar multiplication. It's not closed under multiplication by negative numbers. So if you of course, the subspace generated by this is what you get by extending this indefinitely into a line. So you can take vectors in here and multiply them by negative numbers. But another way to think of it is it's the intersection of, now what are the subspaces that contain this half line? R3 is one of them. Another one is this line, this plane that I've drawn right here. Another one is this little crooked plane that looks like there. And in fact, there's infinitely many planes that I can draw that contain this line. So there it is. So I don't know, maybe one of these is like W1, maybe this is W2, and I should not be enumerating these with integers because there's actually uncountably many. There's more than just a natural number's worth of these planes because there's one for each angle. Okay, so this is a way to define this span. It's the intersection from the top down. You take everything that bigger than this and intersect them, as opposed to taking everything, individual pieces of S, and seeing what they generate. Okay, so let's prove this. Now, the first method's not going to work because I don't really know a good way to express this right-hand side as a set of a collection of elements. I mean, I guess what you could do is you could say it's a set of all vectors in V such that V is in W alpha for all W alpha that contain S, but that doesn't really help. There's no way we're going to get from that up to this definition up here. So that's really not going to work. So what we have to do instead is we have to prove both containments. So let's prove this first containment. So let's take an arbitrary element X in the span of S. So let's say that X equals A1 S1 plus dot dot all the way up to A K S K. So we're just going to take an arbitrary element in here. It may looks like that. And then what can we say? Well, since each W alpha is a vector space that contains S, then by definition, W alpha must contain this as well. So then, since S1 all the way up to SK is in W alpha, X must be in W alpha as well. And there we go. So that we took an arbitrary element in the left-hand side and showed that it was in the right-hand side. If you're not as familiar with linear algebra, you may wonder why I just made that jump, and that's fine. I know at my university, linear algebra is a prereq for this course, and so I think at most students who are taking a discrete math or intro to proofs course will have seen at least some linear algebra, or at least seen the concept of a vector. Okay, so let's prove the other containment. So the other containment, one reason why I really like this example is because the first method doesn't really work. But also, the second method, we can't just do what we've done before, is we can't just take an arbitrary element in the right-hand side, because I don't know how to express an arbitrary element in the right-hand side, yes. I don't know what sort of form it has. Can it necessarily be written as a linear combination like this? I don't know. Like I have potentially probably infinitely many subspaces, mysterious subspaces, that all I know is that they contain S. I don't know how to write an arbitrary element in the intersection. But here's what I do know. I do know that the intersection, so look at this picture here, it's the intersection of all of these W alphas. And notice this. The left-hand side, the span of S, that is one of the W alphas. So this is equal to, I don't know, some W, let's call it W beta. Or if you want to call it W alpha, that's right as well. So let me show you another picture. So here's a collection of sets. This is S1. This is S. Oh, I shouldn't be using S because these are capital S's. So S1, S2, S3. Maybe I should have called these A's. S3. Do you agree with me that S1 is bigger than the intersection of the SI's from I equals 1 up to 3, right? S1 is this thing here, and the intersection is this little piece here. Similarly, I drew it. Let's call that S1 and call that one S2. S2 is also contains the intersection, and obviously every individual SK contains the intersection. Well, we have the same situation here. The left-hand side is one particular W beta. So this is equal to W beta for some beta. And the right-hand side is the intersection, this little tiny thing in the middle of all of those W betas. So of course, this is going to be a subset of that. And that's exactly what we had to show, is that this is a subset of the span of S. So this is one thing that in my experience, I've taught things like this in multiple classes many times. This is something that at some point, more than anything else, it'll click. And if you don't see why what I said proves this right here, please pause the video, rewind it, and see it again. And keep trying it. At some point, you'll click, it'll be like, oh, of course, that makes perfect sense now. It's like a light switch, on or off. And when I get questions about this in class or office hours, I always do. all I can do is just repeat the argument until it sticks. And it's not a gradual thing, it's all at once. So let me try to write this down. Note that span of S is W beta for some W beta containing S. Therefore, span of S, which is W beta, is one individual W beta, is obviously contains the intersection of all of the, I'm just going to write alpha, I'll leave it like this, of all of the W alphas. And I'm just writing alpha instead of rewriting this whole long line right here. And so that's it. This is exactly what we had to show. That proves both directions, and therefore the theorem is complete. End of theorem box. Finally, our last method of proof is by contrapositive or contradiction. So if the set equality that we wish to prove is the conclusion of an if-then statement, so in other words, given blank, if blank, then blank, then A equals B, then we can consider an indirect proof. So we can assume that this is false, and we can prove that this if statement is false as well. Now, I guess for a contradiction, you don't necessarily have to have an if-then statement. If you just want to prove that A equals B, you could assume this is false and then come up with a contradiction, maybe showing that 1 equals 2 or something like that. But I think it's probably more common to see this when we have an if-then statement. And that's the example that I'm going to show you. Let's recall this concept of indirect proof by considering the following statement that we wish to prove. If for all x in the universe, if P of x holds, then Q of x holds. An indirect proof of this can be casted two ways, either by proving the contrapositive or as a proof by contradiction. So, proving the contrapositive, the first statement, so remember the contrapositive just says if Q is false, then P is false. So for the contrapositive, suppose there is some x which makes Q false, and our goal is to conclude that P has to be false. And for a contradiction, we suppose that there exists some x for which P is true and Q is false. And then we want to conclude that P is false. And since we've already assumed that P is true, we have our contradiction. So really, these things are almost the same. I think the main difference is mostly in how you phrase it and how you write it up. For both of these, what you're trying to do is you're assuming that there is an x that makes Q false, and come up with a reason why that also makes P false. We'll conclude this lecture with an explicit example of an indirect proof. So consider the following theorem, which is pretty easy, and like most of these in this class, I think when we wrap our head around it, we'll see why it's true. So let's let A, B, and C be sets. It says if A is contained in B, and B is disjoint from C, then A intersects C or A and C are disjoint as well. So it's obvious from the picture, but again, we should always be wary of proof by pictures. So you could try to prove this directly. So if this holds, then that holds. But it's often hard to prove that a set is empty. How do you prove that there is nothing in the set? I guess you suppose that there is something in the set and you come up with a contradiction, but that is an indirect proof in itself. So let's do that. Let's suppose that the conclusion is false. So this is our Q of x. this is P of x, this is Q of x, so let's suppose that our conclusion is false, and let's show that our assumption has to be false as well. So it's easier to assume that the conclusion is false than is true because if, well, let's write this down. Suppose A intersect C is not empty, and then let's take an element in A intersect C. We're going to take an x in here, and we're going to somehow break one of these two things, show that both of these things cannot hold. So I don't know where we're going to go with this. So let's write this down. Then x is in A, and x is in C. Well, if x is in A, then it has to be in B. Right? So since x is in A and A intersect B, then x is in B. But this means, because we know that x is in B and x is in C, that x is in B intersect C, so B intersect C is not empty. So now we can say, hence, the theorem, oops, how do I spell theorem? T-H-R. Theorem holds since we showed the contrapositive. And there's the last line. Maybe I could have written it a little bit nicer than that, or I could have omitted it altogether. I think you should assume that the reader of your proof has some level of mathematical maturity. So if you're starting with something in this intersection, they should know that you're assuming that this is false, and that all you have to do to reach the end is to show that one of these things has to be false as well.